Hi everyone, my name is Mu Cai, a PhD student at the Department of Computer Sciences, University of Wisconsin-Madison. I will present our paper Auto-distribution detection via frequency-regularized generative models. This work is done with Professor Sharon Yixuan Li. Here, let me give a brief introduction on auto-distribution detection. In a closed-world setting, we always assume that the training and test distributions match with each other. However, this is far from the truth when we deploy our model in an open-world setting, where the training and test distributions can differ a lot. In this case, if a test image is something that the model has never seen before, we want the model to be able to make the decision. This is an auto-distributed sample, and I cannot make any prediction for this image. Therefore, in OOD detection, the key question we want to address is how to build machine learning models that function well in an open world. This is especially important in a safety-critical environment such as autonomous driving.
One way to conduct OD detection is generative modeling. For generative models like VAE and PixelCNN++, the model is trained to maximize the likelihood. Therefore, it should be ideal to use likelihood as scoring function, where OD samples should have lower likelihood.
However, in practice, this is not true. When a generative model like VAE is trained on cipher10, it would assign higher likelihood to OD data such as MNIST images. But why does this happen? Actually, researchers found that current generative models overfit to the trained data, particularly background pixels. Here, we show prior literature on generative-based OOD detection. They try to define test time methods of OOD uncertainty. However, all such methods don't fundamentally change how deep generative models are regularized and optimized. Then, how to force the model to concentrate on the foreground semantic regions? Here, we use a simple representation which pays attention to the high-frequency information. As shown in this figure, high-frequency components care more about the sharp edges and important details, which is essential for OOD detection. Here we adopt basic image transformations, including Gaussian blur and grayscale to represent high-frequency information. In this paper, we propose a simple but effective framework, FRL, frequency-regularized generative models for OOD detection. To be specific, we feed both RGB space image and its high-frequency part into the model to optimize their joint likelihood. FRL provides a general plug-and-play mechanism where similar strategies can be applied to other generative models like GLOW and PixelCNN++, as shown in the bottom.
We adopt a similar score function to input complexity, but improve the likelihood estimation using our high-frequency augmented input. The thresholding mechanism is the same as the prior work. We evaluate FRL across various deep generative models. Besides, in addition to the common benchmark like cipher10 and FastMNIST, we are the first work that evaluates large-scale datasets using deep generative models. In cipher10, FRL achieves superior performance across various generative models. In Sample A, we find that in large-scale settings, generative models including VAE may no longer overfit to the in-distribution dataset, whereas FRL shows stable performance. Across rich ablation studies, we show that high-frequency information is critical, FRL is compatible with different high-frequency representations, and it also improves image generation quality and produces a more concentrated score distribution for ID data. In summary, we propose a novel framework, auto-distribution detection by frequency-regularized deep generative models.
Thank you.